Use the transformation x equals AU, y equals AV, and z equals CW in spherical coordinates to show that the volume of a region bounded by the spheroid x squared plus y squared over a squared plus z squared over c squared equals 1 is 4 pi a squared c over 3. So the first thing we want to talk about here is this transformation here for x, y, and z. So that transformation is x equals AU, y equals AV, and z equals CW. So what I want to show you now is, let's take this spheroid here. I want you to see the region that we're actually dealing with here. So I'm going to take that equation and rewrite it at the bottom here. So this is it here. It's x squared over a squared plus y squared over a squared plus z squared over c squared equals 1. And what I want to show you now is I want to show you what this region looks like. So this here is our region, and notice here that both on the x and the y that it's going to be the same distance. That distance should be a. So this distance here is also a. I just want you to know that because that's a circle if I just slice it at the z equals 0. And when I look at this here, the z is different, or the c can be different here. Could be higher, could be lower. I just wanted to elongate it so you could see that it isn't going to be necessarily going to be the same. So from that this is what my r is, and that's what I want you to see. This is what we're starting with. That spheroid, they call it. I call it an ellipsoid. So anyways, now I want to talk about this transformation. So what I'm going to do is I'm just going to plug this in. I'm going to plug this transformation in to this equation here in this region. So my x, I'm going to plug in AU. So that's going to be AU squared over a squared plus AV squared over a squared plus CW squared over c squared, and that equals 1. So now when I multiply this all out on top here, I'm going to get a squared times u squared over a squared plus a squared v squared over a squared plus c squared w squared over c squared equals 1. And what you can see here is that all of those are just going to cancel out, and I'm going to get u squared plus v squared plus w squared equals 1. And what this turns out to be a sphere of radius 1. So this elongated sphere or ellipsoid that we see here is going to be mapped to a sphere of radius 1. So now let's take a look at that image. Now this is my region S. Now keep in mind here, the transformation doesn't go this way, not at all. It actually goes this way here. It goes back this way. That's what my T is. And we can tell because I have a UA, an AU, AV, and CW here. So that tells me that transformation is going from S to R. So now what we need to do here, once we figure that out, we need to find the Jacobian because we're talking about a volume here. And we're going to actually take the volume of this sphere here, but we need the Jacobian so that we can multiply it by it so we can get the area, or the volume, of this region R. And that's where we're heading to here. So now we need the Jacobian of this transformation that is already set up in terms of TU. This is actually a TUV here. So the Jacobian, so the JUVW here is equal to, it's going to be equal to all of these partial derivatives. Now we're just going to run through each of these. So these are actually going to equal, and I'm just going to run through dx du. Dx du is a, and dx dv, and that's the same one with respect to v, is going to be 0. And also dx dw is going to be 0. And then I'm moving on to the second row now. dy du is 0. dy dv is a. And dy dw is 0. And then for the last row, dz du, and that's this one here, there's no u's there, so that's 0. And dz dv, so that's also 0. And then dz dw, that's going to be c. So this here is my Jacobian. Well, that's my determinant for my Jacobian. So then the determinant of this is actually just one thing here. And I'll show you what that is. I take this a, and it's going to be a times, and then I take the determinant of this here, that's going to be a times c, which is a times c, and then minus 0 times 0. So that's just going to be a times c. Now I do usually put a negative there, but I want you to notice this now, that when I pick this 0 for the second one, I'm going to have to pick these two pieces and those two pieces there, and that's going to give me 0 because I'm timesing it by 0 here. And the same thing for the last column there. I'm going to have to take this as my determinant, but I'm going to be timesing it by 0 ultimately. So that tells me then that I'm just going to end up with a times ac, which this equals a squared c. So that's my Jacobian, JVW or JUVW here. That's my Jacobian for the first transformation. And you'll see why there's another one in a minute. So I have this triple integral here, and I'm just going to write an e there. And I have this Jacobian here. And I'm going to put a 1 here because we're talking about a volume of this three-dimensional region here. So I'm just going to put a 1 there because if I put anything other than a 1 here, this would be a four-dimensional computation. So anytime I'm doing a volume, a triple integral is going to be a 1 for my fxyz. And then I have my Jacobian, which is a squared c, and I'm just going to write dv here. Okay, because now we're going to have to talk about the volume of this sphere here. Now it says use spherical coordinates, and that's where that other transformation is going to come in for us. So now to talk about the spherical coordinates, we have to understand what those are. So this is what they are here. Those are the spherical coordinates. And what we're going to do with those is, remember here, we have a u, v, and w. So instead of the x, y, z that you see here, we're going to use u, v, and w. So my u is going to equal rho sine phi cos theta. And my v is going to equal rho sine phi sine theta. And then my w is going to equal rho cos phi. So we're just going to use these three now for the next transformation. So there's the transformation that we're going to need here. So another thing is now I have to find my Jacobian for this transformation in order to talk about the volume that we're dealing with here. So that means then I need my dx du. Now it's not a dx du for me here. This is actually a du d rho and a du d phi and a du d theta. Now I'm just going to run through the rest of these. So that's going to be the partials with our variables. And I wanted to write those in so there's no confusion of how that goes. So now what we're going to do is we're just going to run through those to get this Jacobian. So for the first one here, du d rho, that's going to be just sine phi cos theta. And then for du d phi, that's the variable there. So that's going to be rho cos phi cos theta, which I see we're not going to have enough room, so I'm going to move it down to the bottom. And then for du d theta, that's going to be negative sine theta for that and everything else. So we're going to get, so that's the first row. I'm just going to run through the rest of these so you don't have to waste a lot of time on a video to see those. You can check them or pause the video if you'd like. So there they are. The last one, just so you know, is dw d theta. And if you can look here, there's no theta, so it'd be 0. So now we're going to find this determinant. Now I'm going to use the bottom row because I got a 0 there. And that 0 is going to eliminate one of my calculations. And I love that because this is a long calculation to begin with. And again, we really only have to do this once. Once we see it, we'll be like, ah, that's nice. And it's good to understand that, of where it's all coming from. It really is. So now I'm going to start here. And then I'm going to take the determinant of all of this here. So that's going to be cos phi times, and now I'm going to times those together. So that's going to be rho squared sine phi cosine squared theta. And then we're going to have to now subtract those two times together. And that's really going to be a negative and a positive. And since I'm minusing, it's going to be a plus here. And then I'm going to get the rho squared sine phi cos phi sine squared theta. And that's the first one. Now I got to go to the middle one here. And that's going to be a minus. I got to negate it to begin with. And since it's a negative already, that means I can write a plus here. So in writing that plus there, I have rho sine phi times. Now again, I'm going to use these two pieces for that determinant now, and I'm going to times those together. And that's going to give me rho sine squared phi cosine squared theta. And then it's going to be minus those two, but that's a negative and that's a positive, so I'm going to be adding those. And that's going to be rho sine squared phi sine squared theta. Now for the last one, I'm going to have to take this and times it by this determinant here, which I'm going to have a 0 there, so I don't really have to worry about that last one. So these are the only two I have to worry about here for this computation for this Jacobian. So now I'm going to have to do some algebra manipulation here. So I'm going to get rid of the rest of this stuff because we're going to need a little space here. So I'm just going to deal with this piece for a minute inside of here. So notice this, that this has a rho squared sine phi cos phi, and this has a rho squared sine phi cos phi. And I'm just going to factor that out of both of those. And there we go. And notice that from that piece there, that cosine squared theta plus sine squared theta equals 1. So that really simplifies things. And then for the other one here, let's take a look at the next one. Out of these two, I can pull a rho sine squared phi out of both of those. And that also equals 1. So now this is going to simplify quickly here. So we're going to get cosine phi times, and I'm just going to write it out, rho squared sine phi cos phi, and plus rho sine phi times rho sine squared phi. And I can multiply these all together and get rho squared sine phi cos squared phi plus rho squared sine phi sine squared phi. And I left those separate because I want you to see here that they both have a rho squared sine phi here. So that means I can pull that out of those two. And that will equal rho squared sine phi times, cosine squared phi plus sine squared phi. And again, this equals 1. So then our final answer is going to be rho squared sine phi. And that's what our Jacobian is for this transformation here. So now we have to think about our triple integral here. So we have to think of the region S now. So we have our triple integral. Let's set that up. We have our region there. So it's going to be the integral, the triple integral, and we have this a squared c from our first transformation. That's our Jacobian. And then we have this rho squared sine phi for the second transformation. And then this goes d rho, d phi, d theta. And now we're just going to have to find the bounds for that. So let's look at d rho first. Now rho is the three-dimensional radius that comes out of the center. So if you think about it, anywhere on the circle, it's going to come out to radius 1. So it's going to start from the center and shoot out. And we're talking about volume here, so we're including all of it. So when we look at that, it's going to come from the in out, and it's going to go out to 1. So it's going to be from 0 to 1 for my rho. Now let's look at phi. Phi runs from the upper z, the positive z, to the negative z, and it's that angle there. So we're going to say that's going to be from 0, and 0 is at the top, and pi is at the bottom with theta, with phi I mean. So phi is going to run from 0 to pi. And then for the last one here, theta is going to take that whole piece there, because that's what I'm doing. I'm going out 1, and I'm taking it all the way down to pi, so it's a sweeping all the way down. It's like that orange slice. And then I'm going to take that all the way around, so that theta is what takes it all the way around. So that's going to be 0 to 2 pi. So there's our setup for this integral now. So this is the triple integral we're going to integrate here. So I'm not going to run through the specifics of this integral, but I do want you to know that this equals 4a squared c pi all over 3. So this is going to be the answer to this triple integral here. And I just want to show you where we started at in this. When we looked at the problem here, notice what it said. It says use the transformation x equals AU, y equals AV, and z equals CW in the spherical coordinates to show the volume of a region bounded by the spheroid x squared plus y squared over a squared plus z squared over c squared equals 1 is 4 pi a squared c over 3. 4 pi a squared c over 3. So we got the same result there. So a very long problem. And 2 transformations later. This is probably the toughest one, I think, as far as like the length.